Last time we have been looking at time discretizations. Now we want to look at spatial discretizations. I would like to give you a brief overview over the main methods, but I want to focus on the finite difference method because that is the method that we are going to use here. So overview over spatial discretizations. As an example, let us consider the following boundary value problem, in fact for an ODE. But that gives us already good insight also what we shall later see when we look at the PDEs. And that is the following. We consider the following. The second derivative of u with respect to x minus of this second derivative of u with respect to x. That is supposed to be equal to some given function f of x for x in a certain interval which I denote xa, xb. Mathematicians usually use 0, 1. And we assume that we have boundary conditions at xa, given, which we call ua, and a boundary condition at xb, which we call ub. So that is our problem that we consider. And for the notation, just to make that clear, the uxx, that means the second derivative of u of x with respect to x. For this problem, we can find the exact solution by integration twice. We integrate twice, then we get minus u is equal to this double integral over f. So we just note that exact solution by two integrations. So that means when we test it, we can use that because we can simply derive the exact solution. Now, as mentioned already, we want to focus on the finite difference method. So that is our first choice. So we use the acronym FDN. So first, we have to make clear what are the number of grid points, what are our grid points, and so on. So some basics. So there we can have different ways of doing it. The way I decided to do it was to look at the number of grid points in the following form, to denote that by nj plus 1. We'll see later on why it's like that. Because already, I cannot say it already now, it means that we have then nj intervals. If we have nj plus 1 grid points, we have nj intervals. And another way would be, as later used on Tuesday, j max. So then it would be, that is also useful when you do the programming. So that is a good way. First, let us define the grid spacing. So this is a kind of repetition what we already saw in the beginning when we looked at the finite differences. And that is delta x. We call it delta x. Because here it's not ambiguous, but later on, when we have space and time, it is important to distinguish. So that is the spatial grid spacing. And that is then for our interval xa, xb, that is then the length of our interval xb minus xa divided by the number of intervals. Or you could also use j max minus 1 there. So we can also write that. It's just a matter of how we define that number of grid points in the beginning. J max minus 1. And what we are imagining here is something of the kind that we have our x-axis, and that we have some our interval xa and xb, and we imagine that we have equidistant distribution of the grid points. So that is what we assume here, so that we divide that in equal intervals. So, and each grid spacing is then delta x. And we shall use a notation, we shall do that now, for the grid points. The following notation, I think we already did that before. That is xj. And that is then, in that case, xa, where we start from, plus j times delta x. And the j is then, in our case, from 0, 1, and so on, to nj. So there you see we have nj plus 1 grid points. And then, in this notation, the xa would be equal to the x0, and the xb would be equal to the xnj. And then we have some grid point at some point, for example here, that would be, say, our grid point xj. If you would use that with the J-max notation, then that would be xj equal to xa plus, then it would be j minus 1 delta x, and then the j would be from 1 to j max. And then we can check in either case. That's always good to check the bounds. J equal 1 in this notation, then we get here a 0, so that means x1 is then the xa in that notation. For j max, we get here j max minus 1 times delta x. Then we have j max minus 1 times this, that gives xp minus xa, so then plus xa gives xp, so that's okay. So that is the alternative notation, but this notation is indicated here. So, what do we do in finite difference method? We approximate the exact solution at the grid points. That is, so we try to find good approximations at the grid points for the exact solution, in that case, of our boundary value problem. So I use this equivalent finite difference, FD, approximations at the grid points. And for that, we use the following notation. We say uj. That is supposed to approximate the exact solution u of our problem at the grid point xj. So that will be our notation. And in that case, if we use the notation that we introduced here with the nj, can note that we know the boundary conditions. So then we only need to determine the solution for x1 to xnj minus 1. So therefore, we need to determine that from 1 to nj minus 1. And the boundary conditions in that case they would be directly boundary conditions when the values itself are given. They are then taken from the problem that we just defined, and that was that the u0 is the value at u of xa, which we noted by ua, and the value that is then u and j, that's the value then at xb, that we denoted by ub. So they are given, but we have then to find approximations for the interior grid points. So what do we have to do? We have to approximate, in that case, the second derivative. That is the partial, in that case it's the pure second derivative, and that we have to approximate. So let's try to do that. How to approximate second derivative of u, and we want to do that at the grid points. So that is the question. We can derive that in different ways. I want to take the derivation by looking at it from the definition of the first derivative. So let's assume we have our grid. We have here our grid points. Let's assume that we are here at xj, here at xj plus 1, and here at xj minus 1. So these are just 3 grid points. And we imagine that we know the solution or an approximation or that we want to determine at the grid points. That is what we want to determine approximations at the grid points. So we don't know them yet, but we want to find how to approximate the derivative. So we assume now that we have values at the grid points which we want to determine. So this would be the uj, this will be the uj plus 1, and this the uj minus 1. So that is the goal, to determine them. Now we want to use those to get a construction, an approximation of the second derivative. What is obvious very easily is when we can get easily the slopes from j to j plus 1, because we know that the grid spacing here is delta x, and this will be the difference. So then we can say that we can determine that very easily, and what we do now, we attribute the slope, the approximation of the first derivative, to the midpoint, in that case between xj and xj plus 1. So we imagine we have here some midpoint, the midpoint, which we could denote by xj plus 1/2. So the index is then between 0, j, between j and j plus 1. So that is a notation that we will also use later on. And then we could say that the first derivative, du of xj plus 1/2 dx, is approximately equal to the slope that we have here, determined by the finite difference when we determine uj plus 1 minus uj, that is this difference, divided by delta x. So that is a good approximation, in fact. in the same way, we can do it from j minus 1 to j. Also there, we can draw easily a slope, and we can a straight line, and then we can determine the slope of that. Again, we have here the delta x, grid spacing, and this is the difference between uj and uj minus 1. So that means we can also determine there the derivative. In that case, we attribute it then to this point here. That would be then the point xj minus 1/2. So here we have xj plus 1/2, but this is then between j minus 1 and j. Halfway with j minus 1/2. So this is our notation. Midpoint in the interval from xj minus 1 to xj. So then we can say, let us then approximate that by the corresponding finite difference, which would be uj minus uj minus 1 divided by delta x. And now we have two approximations of the first derivative. And they are attributed to points that are actually now a distance delta x away from each other. If you imagine this distance here is delta x again, because this is delta x half and this is delta x half. So this distance here in between is again delta x. So then we take the derivative of that, the derivative of the derivative, to get the second derivative. So let's do that. So then we want to approximate the dv of xj dx, and then we say that is the derivative that is squared. The derivative of the derivative, so let's write that maybe also to be sure. We want to do it in this way, dx, and then we have the du of xj dx. So these guys we have now approximated. So then we take that, and then we have that here, the first one, we take then at j plus 1/2, then we use this approximation here. So then we have the uj plus 1 minus uj divided by delta x, so that is this evaluated at xj plus 1/2 minus the corresponding at xj minus 1/2, and that is this one. uj minus uj minus 1 divided by delta x. So then we have these difference of those. Then we have to divide by the distance they are apart, and that we have argued is delta x. So then we see what we get. If we summarize that, we can get the delta x then squared in the denominator by that. So I use this notation. It means that it is delta x squared, it is delta x squared. So so that is what I use, it's common. And then in the numerator, we get the uj plus 1, here we get the minus uj, and here we get the minus uj. So we get minus 2 uj. And here we get minus minus, we get a plus uj minus 1. So then we have an approximation of the second derivative. So that is now our approximation that we get. So then we get from that, call this number 6, that this will be then approximately equal that the second derivative of u of xj is approximated by this finite difference. And that can also be expressed by means of the one of the difference operators that we introduced in the very beginning. We do that also. It's just for a matter of also using these operators. They make this sometimes more compact, right? The difference operators. So I use now this. I introduce this notation. So we have the notation is the delta x squared of uj. So that is, if you have this, it means that you apply this operator twice. And this operator that we introduced before, that does the following. It shifts the index by 1/2 up minus shifting 1/2 down. So that means this uj plus 1/2 minus uj minus 1/2. So that is this. And then we apply this operator to each of these again. And then we get, applying this to this means shifting index 1 up. That means you get uj plus 1 minus shifting also 1/2 up minus uj. And then we have minus, and then we shift everything a bit and index 1/2 down. uj minus uj minus 1. And then we get exactly what we have over there. In the numerator, we get uj plus 1 minus 2uj plus uj minus 1. So that means we can also express our finite difference operator by our finite difference approximation by using this finite difference operator. So that means we have then that delta x uj divided by delta x squared is then exactly what we have over there, uj plus 1 minus 2uj plus uj minus 1 divided by delta x squared. So then we have an approximation of the second derivative. And now we can insert that approximation in the ODE that we want to solve. So now we are using this approximation, this in the ODE. 1. We get at xj, at grid point xj, the finite difference method. That is then, we have minus the second derivative, so then minus this approximation, uj plus 1 minus 2uj plus uj minus 1 divided by delta x squared is equal to the right hand side, and we were saying we want to do that at xj, so that has to be at xj. So this is then our finite difference approximation of the ODE. Minus second derivative of u is equal f of x at grid point xj. Where is this valid? It is valid at all interior grid points. So it means it's valid for j equals 1 to nj minus 1. Of course at 0 and at nj we have our boundary conditions. So then we should think now how to solve that. Well, first we can imagine that we can write this also in a little different form. It is the same, but just equivalent form would be 1 over delta x squared. And then we take this first, because we want to write this in a matrix form, this expression here. So we get uj minus 1, then let's see. Now I have to do another thing, the minus. I have also get the minus in here, so that we'll get a minus sign. And the minus 2uj with this minus gives a plus 2. And then the minus uj plus 1 is equal to f of xj. And that is true for the interior grid points. And now we want to translate that to a matrix formulation. And we use then the boundary conditions. So we are now using boundary conditions when we write this equation for j equal 1. Why that? If we have j equal 1, we will need the u0 here. That is our ua. And we will need it when j is nj minus 1, because then the j plus 1 will be our u and j, the boundary. So there we need, for these indices, we need the boundary conditions. So then, when we do that, the FDM that we derive corresponds to the following linear system. The linear system of equations. So that will be our equation 8. In front we write the 1 over delta x squared, and then we will get here a matrix. We start with j equal to 1, and then we see already here the u0 minus u0 divided by delta x squared. We take on the right hand side because we know that. That is the boundary condition ua. So then this will be then our first component, the plus 2. So we'll get here a 2, and here we will have then our unknowns. Our unknowns will be u1, u2, u3, and so on. And then we will have here in the end u and j minus 3, u and j minus 2, and u and j minus 1. So they will be that will be our last unknown, because u and j is the right boundary condition that we know. So, and this is then the right hand side. First we have to continue with our matrix. We have just now taken this into account. Now we take this into account. So this is j equal to 1. So we have here a minus 1 times u2. So that means we get here a minus 1. And then the rest will just be 0. And that is then equal to f of x1. And as we argued before, we have to take this boundary condition then, to the u0 into account. And that gives them with a plus on the right hand side. The boundary condition was ua divided by delta x squared. So that will be our first row of the linear system. So we translate this, now we have translated this for j equal 1 to this equation, using the boundary condition for ua. Now let us look at j equal to 2. Now it gets easier, because for j equal to 2, this will be then u1. So we get minus 1 over delta x minus 1 times u1. So that means we get a minus 1 here. It is multiplying with this one. The next is the 2 is 2 times here. You get 2 here. That is multiplying u2 and minus 1 times the delta x squared we have already. So that means we get a minus 1 here. And this pattern will continue all the way down. Let's see where we want to go in the end. We want to end up here, minus 1. I write already what we should expect here. Everything will be the same here. So that's the 2 will be in the diagonal, all the way down. And minus 1 will be the upper diagonal, and minus 1 will be the lower diagonal. So you can, let us now look at the u and j minus 2. So then this will be the minus 1 u and j minus 3 plus 2 times u and j minus 2 and minus 1 times u and j minus 1. And the right hand side, that is in this height here, that will be the f of x n j minus 2. And here we have forgotten to write what the right hand side was. That was for x equal to 2. That was simply f of x2. And this pattern here continues until here. So we get the right hand side at the grid points. And the rest here is 0. So now the last row, that is for nj, j equal nj minus 1. So then we get here minus nj minus 2. So that means we get here a minus 1 plus 2 nj minus 1, so we get also the 2 here. And then we get here minus u nj. That is the right boundary condition, gets on the right hand side. So on the right hand side we will get here the f of x nj minus 1 plus the term coming from the boundary condition, which is then the ub divided by delta x squared. So that will be then our last component of our right hand side. And the rest here, we can therefore leave it like that, is just 0. So that means our finite difference method gives us a tridiagonal linear system. Tridiagonal comes from 3. We have 3 diagonals here. The rest is 0. And we need to solve that to determine our unknowns at the interior grid points. And we shall call this matrix A, so that the whole matrix we'll call A. And this will be our unknown vector u, and this is our right hand side F. So 8 corresponds to A, u equal to F. So now u is this vector, u1 to u and j minus 1, and F is the right hand side that we see over there. And the matrix A that we have here, what is that? What is the dimension of that? We can see that by the unknowns, nj minus 1. So that is an nj minus 1 times nj minus 1 tridiagonal matrix. If we had used the J max, it would be then J max minus 2 times J max minus 2. So that would be just the same, because the J max contains all grid points and we don't need the 2 for the boundary conditions. But in our case, we had 0 included, therefore it's like that. And this linear system, as we shall see, can be solved by a very efficient method called the tridiagonal matrix algorithm. And that we'll take later when we discuss, around when we discuss elliptic problems. This is a very simple example of an elliptic problem. So we just note that and we defer that to when we discuss that. It is simply solving this tridiagonal linear system by LU decomposition, lower upper decomposition, without pivoting. So you might remember pivoting from linear algebra. But we'll take that later on. So the linear system, so 8, so this is the, let's say the AU equal F, solved by TDMA, tridiagonal matrix algorithm, which will be presented later. For the time being, we use simply MATLAB. In MATLAB we have a very nice function which does actually this LU decomposition. It does it actually with pivoting. And that is what we have already know. Later I said that also on Tuesday. It's A\F. So you define this matrix A in MATLAB, you define the right hand side F, then the backslash means solve the system AU equal F. And that is the notation for that. You would have a semicolon usually there. So then we have translated our ODE boundary value problem to a linear system by the finite difference method. What remains to be done is to look at the accuracy that we have not yet done. That is what we want to do now. So, that is looking at the truncation error. So the truncation error of our finite difference approximation 7 that can be checked for the exact solution that we know usually by U of x of our problem 1. So then we simply insert the exact solution and try to find the difference with respect to the exact problem. In our case, then the truncation error at the grid point xj with the grid spacing delta x would be minus. Then we insert the exact solution in the approximation, the finite difference approximation of the second derivative. That is then u of xj plus 1 minus 2 u of xj plus u of xj minus 1 divided by delta x squared. Then we would have then minus f of x, but that is not important because the important thing is this approximation. And the exact solution of that would be minus the second derivative. So we subtract that, minus minus, we get plus, and then we would have to check that with respect to the second derivative of the exact solution at the point xj. So that defines the truncation. And then we do what we also did before. We do Taylor expansion around xj for these values to get an expression for that dependent on delta x. So we do Taylor expansion. So that is very similar to what we did also for the first derivative approximations. We do it around x for xj. So then we have the following. We have u of x plus delta x. So that will be the xj plus 1. That will be the u of x plus delta x. So then we have that is then equal to u of x plus delta x. First derivative, du of x dx plus delta x squared half. Second derivative plus delta x to the power 3 divided by 3 faculty 6. Third derivative of x, u of respect to x plus delta x to the power 4. 4 faculty is 24 times the fourth derivative u of x with respect to x plus higher order terms. We shall also need it for the u of x minus 1, that is u of x minus delta x. Then we simply have then to take minus delta x to the power. There's no change here, but here we'll get a minus. Minus delta x squared is not changed, it's still plus delta x squared. Here we'll get a minus, here we'll get a plus, and here we'll get the next one will be a minus. So then we insert that into the Taylor expansion, the Taylor expansion is inserted into the truncation error to get an expression for that. So we inserting Taylor expansion, or we have it for plus and minus will be 2, the Taylor expansions into the truncation error. Now we make it a little bit shorter. We take xj delta x will be equal to, and we start with a minus delta x 1 over delta x squared, then we take the rest. Now let us look at this. So we get both from the ux plus and minus delta x, we get here a u of x. So we get here a u of xj, and we get here a u of xj. That cancels with this one. Right? So that is gone. Next, the first derivative. From this we get it with a plus sign, and from this we get it with a minus sign. When we add them, they cancel. Next is this. We get it with a plus sign from here, and we get it with a plus sign from here. So we get it twice. 2 times this, that gives delta x squared times the second derivative. So that is the first term that survives. And the next term is the third order term. We get it with plus from here, we get it with a minus from here. The sum cancels. This term we get both for plus and for minus, so we get it twice. So we can cancel the 2, and we get delta x to the power 4 divided by 12 times the fourth derivative. So that means delta x to the power 4 by 12 times the fourth derivative with respect to x. And the next actually will be sixth order, because the fifth order will again cancel with a plus and minus. So we will take that into account. We don't need it, but we can do it just for telling you. Next term would actually be in order delta x to the power 6. And we have still now another thing to take into account. That is, we have the minus, we have to check that, and we have this. So we have then taken this, now this. So the minus is there, that's correct. Now we have still to take the plus, the second derivative, that is the exact second derivative, into account to get the difference between the numerical approximation of minus uxx and the exact second derivative. So now we see that we can cancel the delta x squared. So then this becomes 2 and this becomes 4. Another thing that we observe, we get here now minus the second derivative from the approximation, and here we have plus from the exact second derivative. So that cancels. Only this is left. So that means what we get in the end is the following. We get that this is equal to, so the truncation error xj delta x is equal to the minus in front minus delta x squared divided by 12, fourth derivative of u of xj divided with respect to x, plus, and then we would have, if we would write that, order the rest. The other error terms would be of order delta x to the power 4.
Shouldn't it be minus?
You can that, but for the order it doesn't play a role. We can take it as plus. It's right. It would be formally minus, but it's just the sign doesn't matter. So then we do that. We like to do that to see what is the size of that. When we compare different finite difference approximations, then we usually take the first order, the first error term. We really derive that to see what is the factor here. Otherwise, it doesn't play a role. The important thing is this. So that is then the main conclusion for that the truncation error of our finite difference approximation that we considered is of second order, delta x squared. So that is then the conclusion. That means our finite difference method that we derived is second order accurate. So that means when we refine, well, it means first that our approximation to the problem is second order accurate, but it turns out also the solution in the end is second order accurate. That means the error that we get when we solve the problem with delta x and then with delta x half, the error will be 1/4 with the delta x half compared to delta x. Because the error then goes with the defined grid delta x half to the power 2 is delta x squared divided by 4. So that is always a good thing if you have it's better than first order. Okay, so then we have seen now the finite difference method to solve boundary value problem for ODE. Okay, so now we take a break. For those people in the reference group, if you have a chance, please, we could discuss the next first meeting during the break.